Hi. In this next module, what we're going to do is we're going to focus on a particular topic known as aggregation. Now, aggregation is really an interesting thing to think about because if we think about just basic mathematics, right, we learned early on that like 1 plus 1 equals 2, right? And we think we can just sort of add things up and the sum is the sort of the whole of its parts. Well, when we start modeling more interesting phenomena, whether it's in the physical world, the biological world, or the social world, we find that aggregation is actually really tricky. And one of the reasons we model, right, is to get the logic correct. And we find that the logic of aggregation is really sort of incredibly surprising and novel. Now, we already saw that earlier in the previous lecture when we talked about Schelling segregation models, right? Remember, people had these rules that they followed in order to decide where to live based on their tolerance of other people, right? People who looked different than they did. And what we found is that reasonably tolerant people, sort of, individuals following rules that were tolerant, could lead to macro-level segregation like we see in a city like New York or Philadelphia or Detroit. So what we want to do in this next lecture is just construct some very simple models, some toy models. And when I say toy models, what I mean are models that have very few moving parts that help us try and understand some very basic logic about how the world works. And we're going to use these toy models to understand the process of aggregation. So it's going to be simple, but then also sort of mind-boggling in a way. Okay, so one of the core ideas in aggregation goes back to a famous paper written by the physicist Philip Anderson. And Anderson's a Nobel Prize winner in physics, famous physicist from Princeton. And Anderson wrote a paper called More is Different. And in this paper what he says is, look, you can sort of take a reductionist approach. You can pull everything back and look at something in great detail and say, this is a salt crystal, or this is a water molecule, right? Or this is a neuron. But there's something very different when you connect all those things together. And so you can't do purely reductionist science and look at just individual parts and understand the whole. So more is different. And that's really going to be the focus of this module of lectures, is how is it some of the ways in which more can be different. So what did Anderson mean exactly? So the most famous example that people use is this. This is a picture of a single water molecule, right? 2 hydrogens, 1 oxygen. And we can understand all the properties of a single molecule. But one water molecule can't be wet, right? Wetness, the fact that we can put our hand through water and feel the slipperiness, comes about because of the fact that those hydrogen-oxygen bonds are fairly weak, and so the bonds in our hands are stronger, so we can just push through it and feel that wetness. So wetness is a property of a bunch of water molecules, not of a single water molecule, right? But wetness is sort of child's play compared to something like cognition, personality. So think of the amazing things our brain can do, right? But our brain consists of a whole bunch of little neurons, right? There's neurons and there's axons and there's dendrites and there's myelination and all that sort of stuff, right? It's very complicated. But if we break the brain down to its parts, we're never going to understand where cognition comes from, or where personality comes from, or where consciousness comes from. Those are all what we're going to call emergent properties of the system. Now, we're never going to, in these lectures, we're not going to explain consciousness or cognition, but we are going to sort of at least work through how is it that at the macro level, at the emergent level, we can get stuff that's really far more interesting and surprising than we saw at the micro level. Right? So how are we going to do it? What's our plan? How are we going to proceed in thinking about aggregation? Well, we're going to start out by thinking about aggregation of actions. And I'm going to talk about something called the central limit theorem, but we're going to talk about how just sort of actions add up. And that will just get us thinking about this notion of aggregation in a simple way. Then we're going to look at a particular game called the game of life, and we're going to look at a single rule. This is just sort of one set of rules, and just see how that rule aggregates, just to give us a sense of mystery and wonder about how amazing simple things can be when they add up. Right? Third thing we're going to look at a whole family of rules. We're going to look at a class of models called one-dimensional or cellular automata models. These one-dimensional models are extremely simple. You almost can't imagine a simpler model. And yet we're going to find that these very simple models can do anything. Literally anything. So we talked about those classes of outcomes. They can do anything. And then last, just to pull this into social science a little bit, we're going to talk about aggregation of preferences. So when you think about aggregation, you can think about adding up. I think like 1 plus 1 equals 2, 2 plus 4 equals 6, that sort of stuff. We're adding single numbers. But preferences aren't single numbers. What there is, they're sort of, I like bananas more than apples, or I like, Fords more than BMWs or something like that, right? And so different people have different preferences, and we can ask, how do you add up preferences? They might say, why would we want to add up preferences? Well, we want to add up preferences because if we have a small group, if we have an organization, if we have an entire society, oftentimes we have to make collective choices. And so those collective choices have to depend on our aggregate preferences. So what does everybody want? So the way you have to do that, you've got to sort of add up, here's my preferences plus someone else's, what do we get, right? Okay, so what I want to do in this sort of brief opening lecture, just in the next couple of minutes, is unpack a little bit more about what we're going to do when we talk about aggregation. So the first thing, in terms of aggregation of actions, right, when we talked about why you model, right, a bunch of reasons. One of them was to sort of predict points, and one was to understand data. So when we talk about aggregation of actions, we can think about, like, you know, someone's decision to go to a store, someone's decision to get on a plane, right? We can think of, you know, the economy. Think of the U.S. economy. There's 300 million people. Each day, people get up and make choices. And what we see at the aggregate level is sort of the average of those choices. And what we can show with a very simple model is sort of why oftentimes those aggregate choices have a lot of structure to them and a lot of predictability. And we're going to get things that look like this picture. We get, like, this is called a normal distribution or a bell curve. And this bell curve implies with it a certain amount of predictability and understandability. So a very simple model will let us explain a whole bunch of things that happen in the real world. All right. Next thing we're going to want to do is use models to understand patterns. So a lot of what we see isn't just points, but it's distributions of things. It's things flowing. Now this is true in the physical world, the biological world. It's true inside our heads with neurons. It's also true sort of in the social world. So we're going to construct a toy model, a fun model called the game of life. And in this game of life, there's going to be very simple rules. And we're going to start out with patterns. So here's a pattern right here, right? And time moves in this direction, right? And what we can see is as time moves, this weird configuration keeps changing its shape. And then eventually down here, notice that it's in the exact same configuration it was that it started out with, but it sort of moved one down to the right. Now this is what we're going to call a glider, and this is going to be a recurrent pattern in this model. And we're going to see how this thing, which looks like it's living, hence the game of life, is really comes from just simple rules. It comes from one simple rule building on itself. Right. Then, okay, once we've done that sort of simple rule thing, we're going to even go to a simpler model called one-dimensional cellular automata models. And in these models, we're going to show how a very, very simple model where it works as follows. You can imagine a long string of lights, and each light can be on or off. And each light then has a rule whether or not to be on or off based on just two things, whether it's on and off and what its two neighbors are doing. So it could be that it says, if I'm on and my two neighbors are off, I'm going to switch to off. So each light's going to use the same rule, and we're going to see what sort of behavior we can get. What we're going to find is we can get everything. What do I mean by everything? Well, remember what we saw, we talked about what could the world do? Well, we could see equilibria, right? We could see patterns. We could see complete randomness and chaos, or we could see complexity. What we're going to show is those very, very simple rules can generate all four of those. And this is amazing, right? I mean, it's sort of, if you're in the mood to be amazed, this will be an amazing result. So what do I mean exactly? I mean, look at this incredibly complex pattern. Now, you might look at something like this and say, wow, to produce something that complex, there must be some really interesting, sophisticated, complicated underlying dynamics. Well, the answer is going to be no. You can get things this interesting, right, with very, very simple rules. All right. Then the last thing we're going to do, the last lecture in this module, is going to be about aggregating preferences. So what do I mean by preferences? Well, let's suppose there's apples, bananas, and coconuts. And this might be me right here, so let's put a little S here. And it might be that I like apples better than bananas, better than coconuts. So these little greater than signs mean which one I like more than each other. So this apple is greater than bananas, is greater than coconuts for me. Now someone else, like my son Cooper, he might prefer bananas, right, to apples, and apples to coconuts. So different people can have different preferences, and what we want to talk about is how those aggregate. Now what we'll see is aggregation of preferences introduces all sorts of interesting paradoxes and creates all sorts of problems, which is why, at least one reason why, politics is so interesting, because the aggregation of just these simple preferences creates difficulties that don't arise when we think about just adding up numbers. Okay, so big picture here. A lot of what interests me as a social scientist is groups of people, aggregations of people. Now, how do we understand that? How do we understand how societies work, economies work, political systems work, organizations work? Well, you've got to do two things. And sometimes you've got to understand how the parts work, and then you've got to understand how you add them up. So we're going to sort of do that in the opposite order. We're first going to talk about some of the complicatedness of adding things up. That's this module. And then the next module, we'll talk about the parts, like all these individual people in here, right? So to understand the world, we're going to have a twofold approach. First, understand sort of how things can add up. Second thing, understand the parts that do add up. And then the models that follow in this course, right, what we'll do is sort of put all those things together to make sense of things. Okay, so that's the outline for this module. We're going to, play with some very, very simple toy models that help us understand some of the mysterious phenomena we see in the world, and also just some of this sort of, I think there's just some amazing results in here and how simple things add up to create very complex wholes. Thank you.